So, good morning, everybody. Morning. Yeah, that was not bad for day 5. It's been a long conference so far. It's been a great conference so far. I hope everybody's had a great time. And I hope you have some sort of mental capacity left, even this early in the morning. Hope you've all had your coffee and are raring to go. Okay, so this is Iteration Revisited. So this is really, it's a talk in 2 parts. So the first part is about the iteration model that we have in C++ today and some problems that I think we have with that and how we can perhaps come up with something that's a bit better. So that's the first half of the talk, and the second part of the talk is about a library that I've been working on for the last, on and off for the past year or so, a little longer, that explores these ideas and that is available on GitHub and you can use today. Okay, so that's what's on the menu. I hope that's okay with everybody. So Iteration Revisited, let's start by revisiting probably the first loop many of us ever wrote in C++ or in C. So we've got some C array of size 5, and we've got ye olde for loop, right? So we're initializing some index to 0, we're continuing iteration while I is less than the size, we're bumping the index at each iteration, and then we're accessing the ith element of the array and doing something with that. Okay, so if you're anything like me, you've probably written this like hundreds of times over the course of your career. But actually, this isn't the only way that we could iterate over a C array. And perhaps if you come from a C background and you're very comfortable with pointers, you might choose to write it something like this. So this time we're initializing a pointer p to the address of the start of the array. We're continuing while p is not equal to the address of the start of the array offset by size elements. We're incrementing the pointer at each step so that it now points to the next element of the array. And in the body of the loop, we're dereferencing the pointer, we're fetching the object at that address, and we're doing something with that object. But actually, we probably wouldn't write this in C++ today. We might choose to write it something more like this. We can use standard begin, standard end. Standard end in particular is quite nice because if you've got an array of known bound, we don't have to keep that size variable around. It'll just work it out for us. But actually, we probably wouldn't even write this in C++ today. We'd probably write it more like this. And this is immediately starting to look quite a bit more modern, right? And perhaps we'd go one step further and we'd use a range for loop, but a range for loop is kind of syntactic sugar for not precisely this, but something very similar to this. But actually, this little progression from here to here, all I've done is I've changed the declaration from int star to auto, and I've changed the variable name from p to iter. But it really emphasizes something that is, not necessarily obvious about the C++ iterator model. And that is that STL iterators are a generalization of array pointers. In fact, array pointers are the most powerful kind of iterators. Okay, they're contiguous iterators. And so what the STL model does is it starts with array pointers and it generalizes from there to weaker iterator categories. So this is the model that we've had in the library for, 25 years, in standard C++, a little bit before that, as a standalone library, and it served us very well in that time. There are a number of advantages to this iteration scheme. First of all, it's extremely powerful, right? We can write all manner of algorithms that we can think of, right? We can go all the way up to random access, we can do sorts, we can do in-place algorithms, we can write algorithms that write their data elsewhere. It's a really, really powerful model. It's low overhead, right? This was particularly important back in the days when optimizers weren't as sophisticated as they are today, but it remains important today. We're C++ programmers, we care about performance, and iterators are, in general, a low overhead abstraction. This one's perhaps a bit more arguable, but iterators have a sort of natural syntax. They have the same syntax as built-in pointers. If we understand how built-in pointers work, then we understand how iterators work. So there are a number of advantages to the iteration scheme that we have, but there's a pretty big disadvantage as well. And that is because iterators are based on pointers because iterators have the same semantics as pointers. Iterators are just as unsafe as raw pointers. Okay, now as soon as I start using words like unsafe and safe and so on, there's an important question we need to ask, which is, what do I mean by safety? Right, we've heard a lot of talks about safety at the conference, in particular Bjarne's keynote on Monday. So what do I mean by safety? So for the purposes of this talk, there's a definition of safety that I really like. And it comes from this talk by Dave Abrahams. He's actually speaking later today. But he gave this talk at CppCon last year. He was talking about the val language, now known as HILO. And his definition of safety is this. He says, a safe operation cannot cause undefined behavior. And that might be a little bit small on the screen, so I'll blow it up a tiny bit. There we go. A safe operation cannot cause undefined behavior. And I really like this definition of safety. Because once undefined behavior occurs in the running of our program, all bets are off, right? We can no longer reason about the state of our program. The standard imposes no requirements on the behavior. Literally anything can happen. And we've all seen these, crazy lightning talks where the compiler is optimized, assuming that UB is not going to happen, and then we get some absolutely crazy thing happen, and it's very entertaining and kind of terrifying at the same time. So a safe operation cannot cause undefined behavior, because once undefined behavior occurs, we can't reason about the state of our program. It's unknown, it's unknowable, and so really, we can't even reason about any other kind of safety in the presence of undefined behavior. So avoiding undefined behavior is important, crucial, you might say. And so let's have a little look at some code using iterators, and armed with this definition of safety, let's try and decide whether these are safe operations. And, well, I think you can probably guess where this is going, but let's have a look at some examples. Okay, so the first example, I'm taking I'm forming a pass-the-end iterator to some range. This line 1 is perfectly fine, we're allowed to do this. What we're not allowed to do is what we're doing on the second line. That's we're taking our pass-the-end iterator and we're dereferencing that. And if you think about this in terms of array pointers, this makes sense. We're allowed to form a pointer one past the end of an array. In fact, we're given special permission by the language to do that pretty much entirely so that we can iterate using pointers. We're allowed to form the pointer, but there isn't an object there. So there's nothing to fetch, right? So dereferencing a pass-the-end iterator is undefined behavior. Okay, well, that's not great. So what happens if, instead of dereferencing the pass-the-end pointer, we increment the pass-the-end pointer? Well, unfortunately, incrementing a pass-the-end pointer is also undefined behavior. So is decrementing a begin pointer. If we have a bidirectional range, we get a pointer to the start of the range, iterator to the start of the range, we decrement that, it's undefined behavior. So out of bounds random access jumps. We have a random access range, we jump out of bounds, that's undefined behavior, according to the language. So this is not great. But it gets worse. Okay, slightly more complicated example this time. So here we've got a function called miniter, takes a const reference to a vector, and it returns the iterator pointing to the least element in this vector. So this kind of looks as if it's fine. But the problem occurs, what happens if we have a function like getVector that returns by value, returns us a vector by value? Well, what's going to happen now is that getVector is going to return us a temporary. We're going to initialize our const reference from a temporary. And then minElement is going to do its thing. The function is going to return an iterator to the least element of this vector, and that's going to be stored in the iter variable. And then the end of the full expression, the end of the statement, the temporary vector is going to be destroyed, and iter is a dangling iterator. And attempting to do pretty much anything with a dangling iterator is going to end up being undefined behavior. We're allowed to destroy it, we're allowed to reinitialize it with assignment, but attempting to do anything useful with this iterator is going to be undefined behavior. So dangling iterators can occur pretty easily, and as I say, pretty much anything we want to do with it is going to wind up being UB. So far, things aren't looking great, but bad news, it gets worse. And this next example, I absolutely hate. This one upsets me greatly. So can anybody tell me what the problem is here? Iterator invalidation, yeah, magic words. Yes. Okay, so for those who haven't seen this before, what's going on is that we're forming an iterator to the start of the vector, and effectively this is holding a pointer to the start. It's holding the address of the start of the vector's internal storage. And then we call vec.pushback, and if the vector happens to be full at this point, if it's at capacity, this is going to cause the vector to do an internal reallocation. It's going to allocate a new array. It's going to move everything from the old array into the new array, delete the old array, and now iter is left holding a pointer to some deleted memory. Iter has become dangling. And so the next line in the while condition, we're attempting to compare a pointer to the start of some deleted array to a pointer to the end of some completely different array, and we're just not allowed to do this. Right? The language says we're not. This is undefined behavior. So if we have a dangling iterator, an invalidated iterator, we can't even ask the question, like, are you valid or not? Right? And what makes this example even worse is that this is probably going to work. This bit of code on the screen is probably going to work most of the time. This can be sitting lurking in your code base for like 20 years, and it's erroneous, but you get away with it. And then all of a sudden, one day you recompile and someone's changed something like 1,000 lines of code away, and all of a sudden vec is slightly differently sized to what it used to be. And now you're getting the reallocation where you never got it before, and it suddenly hit UB. Ben?
Question. Is this UB even if reallocation does not occur? Is UB equal to the library rules even then?
I believe so. Yeah.
Please repeat the question. There's a microphone for questions up there.
Okay, I do have a lot of stuff to get through, so it's probably better to leave questions to the end if we can, otherwise we're going to be really pushed for time. But the question from Ben was, is this UB even if reallocation doesn't occur? I believe it is, actually. So pushback is documented as invalidating iterators, which is actually ties in nicely to the next point I was going to make, which is that this is particularly bad because if you're a newcomer to C++, or maybe if you're an expert in another language who uses C++ occasionally, there is nothing obviously wrong with this code, right? This looks all right. It looks like it should work, and it's going to work most of the time, but there's a latent hidden bug in there. And really the only way that you can know that this is problematic is because either you've been bitten by it, or because you were very diligent and read the documentation, and you know that pushback invalidates iterators. So iterators can become dangling in non-obvious ways, and really it's all just part of the C++ experience, right? It's just something you have to know. Sorry. So our statement was, a safe operation cannot cause undefined behavior. And yet, as we've just seen, most iterator operations have the potential to cause UB. And if you put these two statements together, really there's kind of only one conclusion you can draw, and it's not a happy one. And that is that STL iterators are a fundamentally unsafe abstraction. And I don't know if you've noticed, but a lot of people are suddenly talking about safety. Right? We've had a few talks this week. We've had government agencies coming out and saying, well, don't use C++ because it's unsafe. And it really doesn't help that one of our most fundamental and important abstractions, isn't great when it comes to safety. So can we do something better? Can we come up with an iteration scheme that is just as powerful as iterators, but doesn't have these associated safety problems? Well, I think the answer is yes, because otherwise I wouldn't be standing here. But before we get to it, let's just have a little look at what such an iteration scheme would need to be able to do. Okay, so we're going to go back to this example with the for loop. And actually, this neatly demonstrates that any external iteration scheme needs to be able to do 4 fundamental operations. Okay? So first of all, we need to initialize some iteration state. So for iterators, this state is encapsulated in the iterator object. Secondly, we need to be able to check whether iteration is complete. So for iterators, we do this by comparing to a pass the end iterator or Sentinel in C++20. Next, we need to be able to read the element corresponding to the iteration to the state. Okay, if we can't do this, we can't really do anything useful with our iteration. So we do this by dereferencing the iterator. And finally, we need to be able to advance the iteration state so that we're now looking at the next element. And then we do check, read, advance, over and over again until such time as the check tells us that iteration is complete. So this is not really new. This has been known for decades and decades. And in fact, if you even just think about the syntax of the for loop in C, a for loop is really just syntactic sugar for a while loop, but it's based around these four operations. Right? Initialize, check, read, advance. And one of the things that's quite interesting is that although these operations are fundamental, we don't actually need to write them as four separate functions. It's possible to fuse together these operations in various ways and get a usable, useful iteration scheme. In particular, some people might be familiar with Rust iterators. So Rust iterators fuse together the check, read, and advance operations into a single function called next, which returns, well, in C++ terms, an optional. So the first time we call next, it returns as an optional with the first element. Second time we call next, it returns as an optional with the second element, and so on, till eventually it returns as an empty optional, signaling that iteration is complete. So this model is kind of interesting. I wrote a whole library implementing this in C++. You can find it on my GitHub. It's an interesting model. It has advantages and disadvantages, the chief advantage being it's much simpler than the C++ model. Right? There's only really one function that you need to concern yourself with, whether you're a producer or a consumer. So it's much simpler. The downside is that because we have fused together these operations, we can't call them separately, we lose some expressive power. Right? There are algorithms that you can't write with the Rust iteration scheme. There are algorithms that you can't write as efficiently as you can with the C++ model. Okay, so while the Rust model is interesting and kind of fun to look at, if we want something that is going to be able to do everything that iterators can do, we are going to have to provide these four operations independently. So as a little aside, if you're interested in this stuff, if you're interested in how different languages, different libraries do iteration, Barry Revsin has this absolutely fantastic talk. He gave it a keynote at CPP Paris a couple of years ago. Really, really, really highly recommend this talk. So he compares C++ iterators and ranges with D ranges, Rust iterators. He looks at Python, C#, Java. It's a really, really interesting talk. If you're interested in this stuff, really highly recommend it. Okay. So now we know what an iteration scheme needs to do. Is there some sort of way of iterating in C++, perhaps one that we're already familiar with, that does all of these things and does it more safely than using pointers? Well, there is. And in fact, every single person in this room is already familiar with it. Right? And I know you're already familiar with it because I snuck it in as the very first slide of this presentation. And that is iteration with indices. Okay? So now we're iterating over a vector using indices. Here's the loop, and you can see that we've got our four operations. We're initializing our iteration state. In this case, our iteration state is the index. We've got our nCheck, checking whether I is less than the size of the vector. And now we're going to define our read operation to be vec.at. We're going to define a bounds-checked read operation. Okay? And then finally, we define our advance operation to just bump the index. So armed with these new definitions, what happens if we take them and we substitute them into those problematic iterator examples that we looked at before? We just perform a literal substitution. What happens? Well, let's have a look. Okay, so this was the first example we saw. So previously we were creating a pass the end iterator. Now we're creating a pass the end index. and then we're attempting to perform our read operation via that past the end index. And now, because we defined our read operation to be bounds checked, this is not undefined behavior, right? This is well defined. This is going to throw an exception. We know what's going to happen. We can prepare ourselves for it. We can handle it. Our second example, what if instead of dereferencing, instead of reading from the past the end index, what if we just perform our advance operation? Well, in this example, index is just a size t. Operator ++ is well defined for all values of size t. So incrementing a past the end index is fine. Right? This is not undefined behavior. And yes, this assumes we're using unsigned indices, or we have some sort of checked operations on signed indices. Actually, the library I'm going to be talking about, we have a whole suite of checked numeric operations, so this is absolutely fine. What about our third example? So this was the one with the min-iter function. So now, instead of min-iter, we've got a function min-index. Imagine it does the same thing. It just returns you the index of the least element in the vector. Okay? It's only a few lines of code, but it's not really relevant, so I've just skipped it on the slide. But now what happens if we do the same thing? If we pass a temporary into this function, well, it's going to do what it does. It's going to return us the index of the least element of this vector. We reach the closing semicolon, the temporary gets destroyed, and then what happens? Then what happens is nothing, because we defined our read operation to be vec.at, meaning that we still need the vector around in order to call the read operation, right? So we simply cannot, it's just not possible to do the bad thing. Right? So this isn't even mitigation. This is just like, we simply cannot write it. So dangling indices are suddenly safe by design. A whole class of bugs just disappears. Okay, what about our last example? This was the horrible one. This was the one I really hated. This is the one that upset me. So what happens now if we use indices rather than pointers? Well, now we initialize an index to the start of the vector, the 0 position of the vector. We push back into the vector. This may or may not reallocate, but we don't care, because either way, we're not invalidating our index. Okay? The last line index is less than vector size. That's always going to work. Index invalidation problems are no longer undefined behavior. And yes, it is, not in this case, but it is still possible to get invalid indices if you're holding on to index number 100 and you resize the vector so it's only got 10 elements. You're going to have an invalid index, but then it's going to be caught by the bounds check at the next attempted read. No undefined behavior. This is great. So index-based iteration dramatically reduces the potential for undefined behavior compared with pointer-based iteration. But it's still just as powerful. Right? We can do random access with indices. Of course we can. We do it all the time. We can write all the algorithms that we would want to write with iterators. We could write them with indices instead. In fact, if you go and look in algorithms textbooks, typically they will give you the algorithm in sort of pseudocode using indices, and you have to then go back and translate it in your head to something using iterators. Well, maybe not anymore. So here's the big idea. What if, rather than doing what the STL does, which is to take the idea of iteration by pointer and generalize backwards from there, what if we took the idea of iteration by index and generalized that? What would that look like? Wouldn't it be great if somebody had done that already? Wouldn't that be nice? Well, it just so happens that someone has. Okay, so as I say, for the past year or so, a little bit longer, I've been working on a library called Flux. The URL is on the screen. The name is not particularly important. The important thing about the name is that it's got an X in it, so it sounds all cool and mysterious. So Flux aims to provide, first of all, much improved safety by default versus STL iterators. That's all the stuff we've been talking about so far. Secondly, it aims to provide improved ease of use, fewer gotchas. In particular, I want to make it easier to implement sequences, ranges. If you've ever tried to do this, you'll know it's a major headache, endless operator overloads in your iterators and things like that. So fortunately, I don't have time today to talk about that aspect, but you can go and have a look at the library. Flux aims to provide runtime performance that is at least as good as C++20 ranges. So if you can afford to use ranges, you can afford to use Flux. And finally, Flux aims to offer compatibility with existing STL code. There are countless millions of lines of code out there using iterators. People have custom algorithms that work on iterators. People have custom containers that provide iterators. We need to provide some sort of compatibility story. Right? I can't just come along and say, start using this completely new thing with no migration strategy. Okay. So we know what our iteration operations need to be. Right? Initialize, check, read, advance. So let's have a quick look at how we perform those operations in the Flux library. So our initialize function is called first. So I couldn't call it begin for obvious reasons. So what's a synonym for begin? Well, it's first. And first returns you an object called a cursor, which represents a position in a sequence. Technically a position between two elements, but represents a position in a sequence. And you can think of a cursor as like the generalization of an integer index in the same way that an STL iterator is the generalization of an array pointer, right? So a cursor isn't necessarily an integer. It can be pretty much whatever you like, whatever makes sense for your particular sequence implementation. But it just so happens that for contiguous sequences, for things like vectors, it is literally just an integer index. Okay, so that's our initialize operation. Our Uncheck is spelled isLast. So this says to the sequence, please can you tell me whether this cursor is past the end, whether I should stop iterating. Our read operation is simply called read_at. So as you imagine, we say to the sequence, please will you give me the element at this cursor position. And importantly, for sequences, this is bounds checked. So by default, the Flux library, if the bounds check fails, it's going to terminate your going to call standard terminate. You can configure the library so that it throws an exception instead so that you can clean up on the way out. And finally, our advance operation is spelled increment inc. And what this does is it takes the cursor by reference and it increments the cursor so that it's now pointing to the next element in the sequence. And what you'll notice actually is that all of these operations, in particular the last three, they all take the sequence as the first argument, meaning that if we are in a situation where we're holding onto a cursor, but the sequence itself has gone out of scope and we no longer have it, it means we can't actually call any of our iteration functions, right? So as I was saying, this whole sort of class of dangling iterator problems just goes away. We can have a dangling cursor, but we can't do anything problematic with it. Okay, Flux is a C++20 library. It makes pretty heavy use of concepts. And a type that provides these four operations that we just saw, we say it models the sequence concept. So again, I couldn't reuse the term range. That would be really confusing. So I called it a sequence. Sequence is also quite an overloaded term, but I had to call it something. So as with ranges, the basic sequence concept is assumed to be single pass. That is, once we've moved on past an element, that element has gone, disappeared into the ether, and we can never look at it again. But of course, we also have multi-pass sequences. So these are the equivalent of forward ranges. Okay, so multi-pass sequences allow us to have multiple cursors, which can be manipulated independently, and so we can potentially read over each element position multiple times. So multi-pass sequences have a couple more requirements than the basic sequence concept. They need their cursor types to be regular types. So that is, they need to be default constructible, copyable, and equality comparable. Right? And this means that in algorithm implementations, we can take a copy of a cursor, we can save that cursor position to come back to it later. We can compare two cursors to say, do you represent the same position in a sequence? So this is how we differentiate between multi-pass and single-pass sequences. If your cursor is regular, then we assume you're a multi-pass sequence. This works really well because it turns out that semantically, cursors for single-pass sequences should typically be move-only. Okay, it doesn't really make sense to have a copyable cursor for a single-pass sequence. But I wasn't really comfortable with requiring something to be not copyable. That's kind of weird. So if you happen to have a copyable cursor, then there's an opt-out, and you can say, no, hang on, I am only single-pass. So going further, we can have bidirectional sequences. So again, equivalent to bidirectional ranges. And these provide an extra function, dec, counterpart to inc, and does what you imagine. It moves the cursor one place back. We have random access sequences. So these provide, again, a couple more additional operations. So we have an overload of inc that takes a signed offset, so we can jump an arbitrary number of places in constant time. They provide a distance operation. So if we have two cursors to a random access sequence, we can say, how many elements are there between these two cursor positions? And finally, cursors for random access sequences must be totally ordered. That is, they provide less than, greater than, less than or equals, greater than equals, right? And so we can say, if we've got two cursors, we can say, is this cursor position earlier or later in the sequence than this cursor position? And then, yeah, finally we have contiguous sequences. These are like contiguous ranges. They're random access. They're backed by an in-memory array. Means we can do, in some cases, low-level operations, mem copies, and things like that. So if you're familiar with ranges, you'll be able to see that there's a very close, these are very close analogs to the equivalent ranges concepts. And it means that we can take our existing ranges algorithms, and really it's almost a mechanical transformation to use the Flux primitives instead. And it makes it really quite easy to take an existing implementation and convert it to the Flux scheme instead. So we've got a whole load of algorithms in the Flux library already. We don't quite have all of the 100 plus that are in the STL. Hopefully we will do at some point, but these are the ones that are in the library today. If you're watching on YouTube at some later date, hopefully we'll have some more as well. So this is all very nice. This is great. We can call algorithms. We can, be confident that we're not going to run into undefined behavior. This kind of puts us in the same place that the standard library was in like 1998. And if you've seen any of my talks before, you'll know that I'm a really big fan of C++20 ranges, right? What people call sequence-orientated programming or collection-orientated programming. The C++20 ranges library provides us with a lot of range adapters, these things people call views, which allow us to build up these data pipelines. And so I wanted to provide the same facilities in the Flux library as well. So like C++20 ranges, Flux provides a variety of sequence adapters which perform lazy evaluation in the same way that views do. And just as with ranges, we typically compose these into pipelines. So a pipeline begins with some data source, some sequence, and then we pass it through 0 or more adapters, which modify how we read the elements of a sequence, and then finally we call some algorithm which is actually going to do the work, actually perform the iteration. And, do some in-place modification or give us some result. So the algorithm might be one of the named algorithms you saw on the previous slide. It might be a user-written algorithm. It might be an STL algorithm, as we'll see shortly. Or it might just be a for loop, right? Because a for loop is just an algorithm you haven't given a name to yet. Doesn't necessarily mean it's bad. It might genuinely be one-shot code, but no raw loops, as a wise man once said. Okay, so let's have a little look at a little example of using Flux, a little example of the syntax. So we've got some vector of integers vec, and what we want to do for this example is we want to find the maximum of the squares of the even numbers in this vector. This is one of these toy examples that you see on slides, but it gives you a nice flavor of what using Flux looks like. So the first thing we need to do is we need to decide how we're going to access the data from our source. So do we want to move the vector into the pipeline? Do we want to take a copy of the vector and operate on that? Or, as in this case, do we want to take a reference to the vector? So Flux is quite explicit about when it references so that you can visually see in your source code where you have data and lifetime dependencies. So in this case, I want to iterate over a reference to the vector. And the next thing I want to do is I want to filter the vector retaining the even numbers. So right away, you can see there's a bit of a difference compared with C++20 ranges because we're using the dot syntax. We're using the member function syntax. So in ranges, this would be like pipe, standard views, filter, and then you'd probably have to provide a lambda. In Flux, we actually have a built-in predicate to select the even numbers. So the choice of using the member function syntax versus the pipe syntax, to be honest, it's not technical, right? There's no kind of performance benefit or anything like that. I could have used pipes. Really, it comes down to two things. The first one is readability. Like I just find using like this dot that dot that dot that. I just find it's a lot more readable than like pipe standard views this, pipe standard views that. I find it's just much more readable. And secondly, it means that in your IDE, if you've got a Flux sequence and you just press the full stop key, the period key, your IDE is going to give you a nice long list of all the operations that you can perform on this sequence. And it's even going to give you the function signature and a line of help text. So this is really nice. And yeah, maybe IDEs one day will get smart enough that you can type the bar character and it will tell you what can go on the right. They're not there yet. Okay, so Flux, as a sort of design choice, uses a member function syntax. So we've got our filter. The next thing we want to do is we want to square every element. So in Flux, this is done with an adapter called map. So the standard library calls this transform, but literally every other library of this kind for any language you can think of, or almost any language, calls this operation map. So we call it map in Flux as well. It also has the advantage that it's nice and short because this is a very common operation. So we're taking our data, we're filtering, we're mapping. Now we want to find the maximum element. So the way we do that is with a call to the max algorithm. We just pop it on the end, just like that. There's actually a bug in this code. I don't just mean the missing semicolon, right? Imagine there's a semicolon at the end. There's a bug in this code, there's a problem with it. Yes? Perfect. What if the vector is empty? Yeah. Or what if the vector has only odd numbers in it, right? What happens then? So actually, there's an equivalent algorithm in C++20, standard range is max. Does anybody know what happens if you give an empty vector or an empty range to standard range is max? Jeff, you probably know. It does not. It is, I heard somebody say it over there, it's undefined behavior. Passing an empty range into standard range and max is undefined behavior. So Flux, we want to avoid UB as much as we can within the bounds of the language. So in Flux, the max operation actually returns you an optional. So if the input sequence was empty, we return you an empty optional. Otherwise, we return you an optional containing the maximum value. And we require the user to handle the empty case. So in this case, I've decided that 0 is a reasonable default. Okay, so this is kind of a toy example of what using the Flux library looks like, using a couple of sequence adapters. In Flux, we have a whole load of sequence adapters that are available. And as I say, if you're watching this at some point in the future, I imagine we'll have some more as well, because I find this stuff really great. I love doing these things. I love implementing these things. So we'll have some more. So we've got equivalents of all of the adapters that are in C++20. almost all of the ones in C++23. There's one I haven't got round to yet, which is join with, but it will be there soon. And as far as I know, all of the adapters have been proposed for C++26 as well, and a couple more besides the set algorithms as well. Thank you, Jerry, for contributing those. So we can compose these pipelines. We can do all of the things that we can do with standard ranges. In fact, we can go a bit further. But talking of standard ranges, one of the important properties of Flux is that I want to offer good ranges compatibility. So to that end, every contiguous size range is automatically a Flux contiguous sequence. Okay? If you have a contiguous range, you can just start using it with Flux without doing anything whatsoever. Right? You can just drop it in at the top of the pipeline, pass it to an algorithm. It's just going to work. The reason we can do this is because contiguous ranges are cheaply indexable. We can access the data pointer and we can offset from there. We can access the size and we can do cheap bounds checking. So this is very nice. This covers vector, array, string, string view, span, initializer list, C arrays, all of these things that you really want to be using. We can just start using them with Flux without doing anything whatsoever. If you have a range that is not contiguous, if for some reason you're not using vector, apparently people do occasionally like to use other data structures, which seems weird to me, but apparently people want to do it. Other ranges, we have this translation function, which is called fromRange. So this takes your range and it wraps it up in the Flux protocol, and it implements these Flux primitives in terms of the equivalent operation on the range's iterators. Okay, so because we're calling the iterator operations, we can't provide the same safety guarantees. This is a bit of a shame. It's no worse than using ranges directly. It means you're not getting the full benefits of Flux, but it is compatibility, and it's the same level of safety you'd already be getting. So this is compatibility in one direction. This is taking your ranges and using them with Flux algorithms, with Flux adapters. What about the other way around? What if I have a Flux sequence and I want to use it with some algorithm expecting a range, expecting iterators? Well, going in the other direction, the news is even better, because every Flux sequence is automatically a C++20 range. Every Flux sequence provides begin and end operations which return you a C++20 compatible iterator, and end will sometimes give you a sentinel, sometimes an iterator, depending on the properties of the range of the sequence, but it is compatible with C++20. So we can just start using our Flux sequences with C++20 algorithms, C++20 range adapters if you really want to, and it's just going to work. And in particular, it means that Flux sequences work with range for loops. You can just say like for int I colon my sequence. It's just going to work. So how do we do this? Well, we've got this class template sequence iterator. It holds a pointer to the sequence and the current cursor position, and then it laboriously implements all of these many, many operator overloads. I can't remember how many there are, 40 or something, all properly constrained depending on the properties of the sequence. And so our ranges, functions, algorithms can operate on sequences. So yeah, this is holding a pointer to the sequence. It can dangle. It can become invalidated. But this is iterators. We're used to that. Okay. Last little section now. We're actually doing pretty well for time. I should have allowed Ben's questions. There's one last thing I've got to talk about that you've, well, probably because I told you to be quiet, but you've all politely been ignoring, which is this guy. And this guy represents performance. Because when I've talked about Flux before, and I've said that, well, our read operation is bounds checked, and I can almost see people start to tense up, right? Because this makes people nervous. People are like, oh, well, there's like, we're going to be doing something extra for every single element in my sequence. You're going to be doing more work. This is bad. Well, it turns out that compilers are incredibly good at eliding bounds checks. Really, really good at it. And part of the reason for this, I think, is that pretty much any new language you can think of that's come around in the last, I don't know, 30 years, probably longer, whatever their native built-in array type is, it's almost certainly going to be bounds checked, right? It's really hard to think of a language that's come around in the last few decades that doesn't have bounds checking. And this means that optimizers are really, really good at recognizing this pattern and removing the bounds checks. So I've got a little example. This is might be a bit hard to see unless you're in the front row, but what I've got is a function called count evens, and what this does is we just iterate over a vector with a for loop. If the element is even, we bump our count, and then we just return how many even elements there are. So this is the kind of classic imperative version, and then I've got a version that uses a macro called Flux4. This is mostly something I use internally for testing, although it is available if you want to use it. And what this does is it does the equivalent iteration, but it uses the Flux primitives that we were talking about, read at, inc, etc. So again, if you are close enough to be able to see this, you can see that, okay, we're not getting precisely the same code. The compilers decided to lay things out on different registers, but the inner loop is the same shape, right? And actually, if you benchmark this code, you'll see that there's really no difference in performance whatsoever, right? It's just, any difference just works out to be noise. But as I mentioned, this implementation that we just saw, this is using this macro Flux4, which is kind of ugly. It's mainly, I just use it for testing, right? Because for end users, the idea is idiomatic use of Flux, if you can have idioms in a new library, right? I guess I get to decide the idioms. Idiomatic use of Flux, recommended use, would be to use a named algorithm where one exists, rather than doing manual iteration. So what happened, so happens that in this case, we have an algorithm that does exactly what we want, namely COUNTIF. So what happens if I use COUNTIF rather than this ugly Flux4 macro? So here it is again, except this time I've changed the Flux code, so it's just a single line. It's just calling Flux COUNTIF and passing the predicate. And now if you look at the generated code, so Flux is on the left, you can see that it is 100% byte for byte identical code. Okay, the only thing that's changed, the only diff, is the function name. This is 100% identical to what we get in the imperative case. So, okay, hang on. What magic is happening here? The magic that's happening is something called internal iteration. So this is an extra facility that Flux has, in that sequences can provide this extra optional customization point called for each while. For each while takes a predicate and it instructs a sequence. Please will you iterate over your elements in whatever is the most efficient way you know how to do it until such time as the predicate returns false. And it turns out that many sequence implementations can do internal iteration more efficiently than by calling check, read, advance in a loop. And many sequence adapters can do this efficiently by calling for each while on their parent sequence and providing it with a modified predicate. And this actually leads to, and we can write many algorithms in terms of a call to for each while. So a whole class of algorithms where you begin at the beginning and just keep iterating until some point. Almost all of those can be written in terms of this for each while function. And by using this internal iteration, it turns out we get, in many cases, much better code generation than would be possible with sort of a naive read, check, advance loop. Okay? And this means that in many cases, Flux pipelines can actually generate more efficient code than the equivalent C++20 ranges pipelines by using this trick of internal iteration. So I've got a little example of that. I've got a ranges pipeline here, so we're taking a vector, we're filtering, retaining the even numbers, we're squaring each element, and then we're calling standard accumulate to sum up the squares of the even elements. Okay? And then I've got the equivalent Flux pipeline, so we're taking the vector by reference, we're filtering, retaining the even elements, we're squaring each element, and then we're just calling this function called sum, which, as you might imagine, sums up the elements. So if we look at the generated code, again, Flux is on the left, the ranges code on the right, we can see that, actually, the Flux code seems to be generating an awful lot more assembly than the ranges code. But if you look very carefully, and perhaps the people in the front row will verify this, the Flux code on the left has all of these lovely AVX instructions, right? For the Flux version, because we've had this internal iteration code path, the compiler's been able to see right through all of our abstractions and auto-vectorize the loop, whereas it couldn't in the ranges case. So we've actually got kind of better code generation and likely faster runtime in the Flux case. Okay, so if we're in this happy case where we're able to use internal iteration, we can use this for each while. Typically, we don't need to do any internal bounds checking, right? Because we're not exposing any curses to the user. It's a single function call, so the users can't mess with the sequence while we're iterating over it. So we typically don't need to do any internal bounds checking. In many other cases, the compiler is very good at optimizing away bounds checks. In particular, if you just begin at the beginning and iterate all the way through. Compilers are super good at that. And even if it can't optimize it out, if you're doing anything even sort of vaguely expensive in your loop, then even if the bounds check remains, you're probably not going to notice it. But what about corner cases, right? We're C++ programmers. We care about every last drop of performance, right? What if there is a case where you've measured, you've looked at it, you've profiled, and you can see that, hang on, the bounds check, maybe it's making me 1% slower, and for my particular use case, I can't afford 1%. What happens then? Well, if bounds checking does lead to unacceptable overhead, we have an alternative to read at. It's called read at unchecked, and it does exactly what you think it does, right? It performs the read at operation, but without doing any bounds checking. And the idea is that this can be used selectively where it's needed, where you've measured. So by default, you're going to get the safe thing, you're going to get the bounds checked operation. If you really need it, you can reach for the unchecked version. We're flipping the default to what, in my opinion, is a better default. And you can think of this as kind of the equivalent of an unsafe block in other languages, right? Read at unchecked is an unsafe function. It can lead to undefined behavior. But if you really need it, it's there for you. Okay, so that's pretty much the end of my talk. So Flux is a C++20 library for sequence-oriented programming, collection-oriented programming. It can be used everywhere C++20 ranges can be used. It supports all major compilers, provides improved safety, improved ease of use, compatibility with existing code, and in many cases, better performance than equivalent standard ranges code. So that's my sales pitch. I hope I've done a reasonable job. So thank you very much. So unexpectedly, we do have there's a rush to the microphone. Wow. Okay. Please, go ahead.
Thank you for your talk. Do Flux cursors work with associative containers? And if so, what does the cursor store internally?
Okay, so this is node-based containers in general, right? So a linked list is kind of the simplest node-based container we can think of. So yes, Flux works with these. So you can just take a standard list and use the from range function. That just works. The problem is, how do we iterate over a node-based container safely? This is a tricky problem. There are a few different approaches that you can use, because fundamentally it comes down to, right, our iteration state is like a node pointer, right? So how do we kind of ensure that nobody's messed with our node pointer, like there's still an object and the next? How do we do that? It's tricky, right? There are a few different approaches. You can use shared pointers or lock a weak pointer, and that works. It comes with some overhead. Another approach that works pretty well is that you can have like a generation ID in your linked list implementation. So every time you modify the list, it bumps the generation ID, and then your cursor stores the list generation of when it was created, and then because you have to provide the sequence object for all of your iteration calls, the first thing we do is we compare the generation ID, and if they're not the same, we error out at that point, right? So we never actually get as far as attempting to perform the undefined behavior. Okay, so that's a way to do it. Unfortunately, we can't do it with standard list. We'd have to modify that. But it is absolutely possible to do it with the Flux model.
Hi, great talk. I was wondering if you could give an example of the internal iteration. I get the general concept, but it's hard to wrap my mind around how exactly a no raw loops iteration would be faster than the naive iteration. Do you have a code example or something that you could point to be like?
Not that I have available to give to you now, but the basic idea is that the algorithmic complexity is the same, right? We in terms of the total number, the total complexity, we've still got order n in each case. But it just turns out that if you have an algorithm that calls for each while, and you've got a sequence, and each one of those implements for each while, each of those sequences can do it by calling the equivalent function on its parent and providing it with a modified predicate. And so it turns out that the compiler, and you typically do this with a lambda, and it turns out the compiler can just sort of inline all of these lambdas, and you end up with much better code generation. The compiler is just better able to see through it. So it's not like an algorithmic difference, it's a code gen difference.
Cool, thank you.
All right, so a question about the exposing the cursor and the sequence, and you need to provide those together. Do you expose those to the user for like some of the earlier algorithms you showed, and if so, how do you determine that the cursor is being used with the proper sequence?
Yeah, good question. So you can, if effectively, it's up to the user to get it right, but we require that if your cursor doesn't match up with the sequence that you thought it did. So, okay, sometimes it is really handy, like if you've got a vector and I've found that I've got two vectors of the same size. Sometimes you do genuinely want to use the same cursor with a different sequence. And sometimes that's fine, and sometimes that's actually a really useful thing to be able to do. Other times it's problematic. We require that synchronous implementations don't give you undefined behavior in this case. It might not give you the right answer, but it's not going to be UB. So it's kind of something that you as the user have to.
Okay, so it's giving you security, safety, but not necessarily correct.
Yeah, absolutely, yes.
Okay.
Yeah.
Question on the bounds checking.
Yeah.
So most of us have probably seen that compilers have started warning about this is an out of bounds access. And once you start using .add, that wouldn't happen anymore, right? Because there is this branch before that happens where it throws. So the compiler wouldn't be able to see the out of bounds anymore. Instead, it would throw without a branch before it. So an unconditional throw. Have you considered asking the compiler, do you know at compile time the index and the size? And if yes, if it's out of bounds, make it ill-formed?
So actually, if you try to do it in context per code, it is just going to be ill-formed, right?
Yeah.
Because we can't have undefined behavior.
Because you can't throw.
We can't throw.
But that, I guess,
compilers have started doing it for built-in arrays where they know the size at compile time. And that's great, but that's sort of just a very narrow use of this. And Flux aims to do this kind of more generally for all kinds of sequences, right? Even the ones where the compiler can't see through at compile time. So you're correct in a sense that yes, we wouldn't get the warning in the C case because we are like manually doing the bounds checking.
In any case, I have an implementation idea for you. I can post to the Discord how to get a compile time error in the case where the compiler would know.
That sounds very interesting. Please do.
Right, because what happens, you said compilers become better at bounce checking. They generally just become better at constant propagation. And even if they cannot propagate a single constant, sometimes internally they propagate a range of possible values, and then they still know. In that case, I guess it wouldn't be easily possible to have this kind of check in library code, but certainly an interesting question to how to do that.
It does sound interesting. Yeah, please, we'll talk about it afterwards. So I'm very sorry, I can see there are several people with questions. I've been told the session is over, but I'm going to hang around here. If you want to come and ask me, please do. I'm happy to talk about this for literally the rest of the day. So thank you very much, everybody. Do appreciate it.